Okay, so we were saying that we will deal in this course with closed systems and open systems. So whenever we talk about closed systems, then we have only transfer of energy through heat and work, while when we consider the open cases, then we have mass flux coming in and getting out, and this mass flux will transport energy in and will take energy out of the system. So if we take the example of a duct, okay, let's say if you have water at a certain temperature in your duct. Initially, for example, the temperature is 20 degrees, and then you will have a mass flow rate of water entering the duct, but now at a temperature of 50 degrees. So what will happen then, this mass flow rate that is coming in will transport energy by convection within the duct, and then the temperature will gradually change in the duct. It will increase because you have a flux coming in that is increasing the energy of that is present in your system, and the temperature at the outlet will be between 20 and 50. Now if you keep this phenomena for a long time, at the end you will be able to reach like a steady state behavior where you will have 50 degrees along the whole domain. Okay, but during the transient process you can have transport of energy, and the energy that is coming in is larger than the energy getting out, which will lead to an increase in temperature within the duct system. Let us consider an example where we can that involves different heat processes. A long conducting rod of diameter d and electrical resistance per unit length r prime e is initially in thermal equilibrium with the ambient air and its surrounding. This equilibrium is disturbed when an electrical current I is passed through the rod. Develop an equation that could be used to compute the variation of the rod temperature with time during the passage of the current. So here we can see how the electrical energy will be transformed into thermal energy, and then this thermal energy can be convected out of the system by convection and radiation. So if we consider the question, we want to find the variation of the rod temperature with time. So we are searching for derivative of temperature with respect to time. Whenever they ask you about this, you should think about writing the energy balance of your system. And then when you do this, you can figure out the storage term, because the storage term is related directly to the temperature variation with time. Okay, so the first step will be to consider a certain control volume. Since they are asking to find the rod temperature variation with time, we should consider, let's say, any part of the duct, and we'll see together, okay, that the lengths will cancel out. It will cancel out from the analysis. So let us consider a certain any length L, and we have a certain diameter D for the rod. And they told us that generation is due to electrical generation that will, so electrical energy that will be transformed into thermal energy. You know that by F a joule, the power of generation from due to electricity is equal to the voltage, okay, times I. And the voltage is resistance also times I. So in total, the electrical power is Ri squared. And since this electrical power will be transferred by thermal effect, so we can consider that E dot generated is equal to Ri squared. But in this problem, they gave us the resistance per unit length. So we can replace R by the resistance per unit length, which is R prime electric, times the length of the rod. So this is equal to R prime electric times the length of the rod times the intensity square. This is concerning the generation term. Now, concerning the storage term, how can we write the storage term here? What is the formula of E dot stored? Who can tell me? How we calculate the storage term? No answer? We have already seen what is the formula for E dot stored. Okay? How we calculate E dot stored? We said that it's equal to M Cp times the gradient of temperature with time. And you know that the mass is equal to rho times the volume. So it's rho times V. So we can say here that the energy stored is rho VCP times gradient of temperature with time. Okay. Now, what is our volume? The control volume here is this one. And the volume will correspond to the area, the cross-sectional area of the duct times the length L. And the cross-sectional area of the duct is pi d square over 4. So the volume is pi d square over 4 times the length L. Okay. Now, next step, we consider what are the sources of energy in and sources of energy out. Here, in this problem, mainly you have energy that is transferred out. Okay, you don't have energy in, you just have storage, generation, and flux of energy getting out of your rod. And this will happen because the rod will be heated due to the electrical generation. So it will deliver heat outward through convection to the air and radiation with the walls. So this is why I will divide E dot out into two parts. So E dot out here will be divided into E Q dot convection plus Q dot radiation. Okay. Now, all we have to do is to express these two fluxes, function of the parameters that we have. We have already seen that Q dot convection is related to the convective coefficient H, to the temperature T infinity, to the temperature T of the surface. And we can write Q dot convection as H times A times temperature of the surface minus T infinity. And concerning the radiation flux, we know that we have radiation between the surface of the rod and the surrounding. So we can calculate the net radiation because you have a part that is absorbed and a part that is emitted. But here, the net flux will be out or in for radiation. Who can tell me? The net flux will be out or in here?
Out, doctor.
Yes, it will be out because the temperature of the surface is larger than the temperature of the air and larger than the temperature of the surrounding. So if I want to calculate the net flux, all I have to do is epsilon sigma times T surface to the power 4 minus T surrounding to the power 4. And this is the flux, but if I want the rate of energy in watt, not in watt per meter square, I should multiply by the area. So I should multiply also by A. And now all I have to do is to write the energy balance and replace in the energy balance all of my terms. So now I'm ready to apply the energy balance, which is E generated minus E out is equal to E stored. And as we mentioned, the storage term is in the following form. Here, because we are assuming that for the whole volume, we have the same rate of change of temperature. This is why we are taking rho Vc outside of the derivation. And we are considering that we have the same rate of temperature variation within any point in the rod. Okay, so this is why we can write it as rho Vc times derivative of temperature with respect to time. And as we mentioned, the volume is pi d squared over 4 times L, and E generated is I square R prime electric times L. So if we plug in our equation, we'll see that L will cancel out Y, because we have that the lateral area for which we have convection and radiation is equal to the perimeter of the duct times L. So this is the area that is doing interaction with the surrounding. It is the surface of the rod, the lateral surface of the rod. So this is why, as you can see, L will figure out in all of our terms. It is here in the generation term, in the convection term, in the radiation term, and also in the storage term. So this is why the rate of temperature variation with time is independent of the length. It will only depend on the diameter of the rod. And of course, it will depend on the convective coefficient, the specific heat, the electrical resistance, etc. Now, if we do a small analysis of the terms of this equation, we can see the physics of the problem. Of course, the rate of change of temperature with time will be affected with the electric generation. Larger is, if you want the heating by FA joule, larger will be the temperature variation with time. So for larger resistance and larger current, the rate of change of temperature will increase. On the other hand, the convection play a role into reducing this rate of change, because larger the convective coefficient, you will be able to dissipate this heat and reduce the change in temperature of your rod. So also this is very physical. So as H will increase, we are taking more heat outside of the rod. So the variation of temperature with time will be reduced. And larger is the gradient of temperature, T minus T infinity, between the rod and the environment, will be able to take heat more and more. So also the rate of change of temperature with time will be reduced. The same for radiation effect. If you have larger emissivity of your surface, this will reduce the temperature change with time, because you will be able to evacuate more heat from your rod. Now, concerning the capacitance of your system, larger is rho C, okay? Lower will be the variation of temperature with time, because you know that thermal storage will oppose in general temperature variation. Any question on this? Okay. Let us consider another example. Consider a mass m of ice that is frozen. The ice is at the fusion temperature, which is Tf equal to 0 degrees, and is enclosed in a cubical container of width W on its side. The container wall is of thickness L and thermal conductivity K. If the outer surface of the wall is heated to a temperature T1 larger than Tf to melt the ice, obtain an expression for the time needed to melt the entire mass of ice. In this problem, we'll see another type of energy storage. In the previous problem, the energy stored was in form of sensible heat. Here we have energy stored in form of latent heat. So if we consider what is happening here, first, we'll take the system. Our system is the ice, okay? And our purpose is to find what is the total time needed to melt this ice. So this is equivalent to find first what is the rate, if you want, of storage. Okay. And once we find this rate, we just have to multiply by the time in order to get the energy, because energy is power times time. Okay. So first, we should know what are the type of fluxes or type of energy transfer in this problem. If we consider this control volume of ice, we have heat that is coming in through which type here? You have walls that you have walls surrounding the ice, and we know that in solids, okay, the main mode of heat transfer is conduction. That's why heat will be transferred towards ice by conduction effect, okay, from all sides. So since we have a cube, then you have to consider conduction from all sides of the cube, okay? And we know that conduction is calculated, conduction rate is minus K times A times dt by dx. Okay, so here we can say that, and we know that always heat will go from a higher to lower temperature, so it will oppose the gradient of temperature. So we can write then that it's equal to K times A times T high minus T low over the thickness here, over the thickness of the cube, okay, here, which is, they gave us the value of the thickness here. Let us check for the value of thickness. Okay, it is L. Okay, so here they didn't give us numerical values. We want just to find a general formula. So we will express the thickness as L. Then we have that Q conduction is equal to the conductivity K, the area here. What will be the total area of conduction? You have 6 faces, okay, and for each one you have the width W. So for each face you have W square. And since we have 6 faces, so we'll have a total area of 6W square. So K times 6W square times delta T, T high minus T low, so T1 minus TF over the length L. So this is the total Q conduction. And this is the conduction flux coming, the conduction rate coming in. Okay, in what? So we can say, because of conservation, if we write the energy equation here for this problem, we can start by writing the general energy equation, which is E dot stored equals to E dot generated plus summation of energy coming in minus E dot out. Okay. Now, can you tell me, do we have here a generation in this problem, a generation of heat within ice? Dear students, do we have a generation here of generation of heat in this problem? We have any source that is generating energy? In general, when we talk about generation of energy, we have, let's say, a chemical reaction, or we have, let's say, a electrical current through a wire. We don't have any source here, so we can cancel out this term. Okay, we just have energy coming in by conduction, and also we don't have energy getting out. So these two terms will cancel out. We just have that energy dot storage is equal to energy dot in. So we can replace now energy dot stored by the mass of ice that will melt if you want. So we have m of ice that will melt times latent heat of fusion. And since we need a power term, we should divide this by delta T. So over the time needed to melt the entire mass of ice equals to Q conduction and so now if we replace Q conduction N by its expression, the only unknown in this equation is the time delta T needed to completely melt the ice. So we were able to express delta T function of the mass of ice, the latent heat of fusion, the conductivity of the material, the width of the cube, and delta T and thickness of the cube. Now, of course, if we want to do the analysis of the final result, we can see as expected that the time increase with the mass. Larger is the mass, larger is the time you need to melt completely your ice. And larger is the latent heat of fusion. You need to provide then more energy, and this will require more time. Concerning the thickness, if you have a larger thickness for the cube, this means that you will have a higher resistance to conduction. This is why you need more time to melt ice. Uh, while on the other hand, if you have larger W, so you have a larger area that is allowing heat to come in, this is why increasing W will reduce the melting time. Increasing the conductivity will also facilitate the heat transfer by conduction. So this will reduce the melting time. And larger the temperature difference you impose, larger the conduction rate, and lower will be the time needed for complete melting. So the equation illustrates the physics of the problem. Now, as we discussed, it's very interesting always to take an interface energy balance, because when we consider an interface energy balance, we'll be able to relate the fluxes through the surface. So we can see here, for example, as we discussed, if you have a wall and you have conduction of heat through the wall, this flux of conduction can be transferred to the environment through radiation and convection, or also through, let's say, um, you can have free convection, you can have natural convection. So you have several possible types in which you can get rid of this heat. Sometimes it's only radiation, or sometimes only convection, and other times it's combination of both. So it depends on the problems that you have. Okay. For example, if you have water flowing over the surface, water will be opaque to radiation transfer. So in this case, you will have only heat transfer by convection. While here, you have just air blowing on the surface, so you can transfer out this heat by both radiation and convection. Let us take an example on calculation of heat transfer from a wall to the surrounding, or here from a pipe system to the surrounding. A non-insulated steam pipe passes through a room in which the air and walls are at 25 degrees. The outside diameter of the pipe is 70 millimeter, and its surface temperature and emissivity are 200 degrees and 0.8 respectively. We want to determine the surface emissive power and the irradiation. So to start with, we can draw the system. So we have a steam pipe. We know that the surface temperature no, sorry, the room air temperature is 25 degrees. So T air is equal to 25. and the surface of wall temperature is also equal to 25 degrees. So we can say here from the given, they gave us the temperature of air and they gave us the temperature of the wall. So we can consider heat transfer from the steam pipe to the surrounding by both convection and radiation effects. So we have Q convection and Q radiation. Now, they are asking us to find first the surface emissive power and irradiation, knowing that the outside diameter of the pipe is 70 millimeter and the surface temperature and emissivity are 200 degrees and 0.8. Knowing that the coefficient associated with free convection and heat transfer from the surface is 15 watt per meter square Kelvin, we want to find the rate of heat loss from the surface per unit length of the pipe. Then we will deduce the conduction rate per unit length of the pipe surface. So here they asked little bit in details what we want to do, but we can do it without no need to ask us what is the surface emissive power and irradiation. We should know that this is needed in order to calculate the conduction rate per unit length. Okay, so what we will do here, we'll do an energy balance on the surface. Okay, so as we know here in this problem, we have heat loss to the environment through convection and radiation. And this is why we can say that the total Q out can be divided into a Q convection plus Q radiation. And as we mentioned, Q radiation is the net power that is getting out. Okay, so all we have to do is to do epsilon sigma A times T surface to the power 4 minus T surrounding to the power 4. So here they did the calculation in detail. They started with the emissive power, so the part that is emitted is epsilon sigma T S4, while